Okay. James,
Hi.
I have permissions. I think I've just started it.
I think you have as well. I just got like a notification.
That's unfair. How come Jack has permission and I we have literally the same job?
was here a month before you. I don't know.
That was when they handed out the Zoom invites.
All right. Well, I think everyone is here, so we can start. Please welcome Bobby Bickley. He is a PhD candidate at University of Victoria. He's in his final year, so he'll be graduating soon and looking for jobs. He's got a bachelor's in mechanical engineering from Connecticut, and now he's doing his PhD. He's interested in all things galaxy evolution, mergers, black holes, and particularly application of machine learning to study all of these things. He also had an internship at Max Planck Institute to use machine learning to investigate optical characteristics of X-ray galaxies. So please welcome Bobby. It'll be exciting.
Thank you so much, Liza. I appreciate it. And thank you all for having me here. It's really cool. And yeah, grateful for the opportunity. I will start sharing my screen and then go over to the slideshow. Is that showing up okay?
Yeah, everything is good.
Okay, great. Thanks. Yeah, so as suggested by the abstract and title in the email that went around, I'm going to be talking about some very new results that I have looking at X-ray AGN in the galaxy merger sequence. So this is kind of springboarding off of a couple other projects that I've worked on over the course of my PhD. The first sort of piece of that is post-merger identification, and I'll talk a little bit about the process of doing that and why that's an important part of this study. And also data from the eROSITA space mission. So this is a result of my having a chance to work with folks at MPE outside of Munich earlier this year. So I've been able to use the data from that project and combine it with some of my old methods to come up with hopefully some exciting new results about AGN triggering and accretion in galaxy mergers. As I said, these results are really new in the sense that I'm still sort of working out details of some of the methods. And so I want to say early on that I would really welcome in the Q&A phase of the presentation some feedback or any thoughts that you guys have about the procedure or the results. But I'll start out with a bit of context, and that is to say that in a general sense, we're pretty confident that mergers between galaxies, particularly major mergers between galaxies, alter the evolutionary trajectory of the participant galaxies. And this happens in sort of myriad different ways, almost simultaneously, although the timescales of the different effects are certainly a little bit different. So we see in merging galaxies and coalesced galaxies, enhanced star formation. We see obviously morphological transformation of these galaxies, both in the starlight and in the distributions of gas in these galaxies. As a result of that redistribution of material, we see an enhanced accretion frequently onto the supermassive black holes in the participant galaxies in the case of galaxy pairs, or into sort of the new mutual nucleus in a post-coalescence system. And all of this activity, the enhanced star formation, the AGN, can lead, and there's been some recent evidence showing that it does often lead to eventual truncation of star formation when the gas reservoir of the participant galaxies are basically exhausted or heated to the point that they can no longer form stars by the AGN, or removed through like ejective feedback. So this effect, or all of these different effects, are pretty straightforward to study in spectroscopic galaxy pairs. So you can use something like SDSS, or just in general redshift survey. You can identify galaxy pairs that are closely separated on the sky and also closely separated in redshift, and make some assumptions about their relative sort of projected separation and velocity relative to each other. And study the characteristics of those galaxies sort of as they approach each other. Even though galaxies on the sky are basically frozen in time, you can study them as they approach each other in a statistical way by taking galaxies that we assume to be at different stages along the merger sequence. Excuse me. However, the problem with doing that is that we think from some of this evidence, and I'll show you some examples of this on the next slide, we think that the biggest changes ushered in by a merger event happen after coalescence. So this is to say, after the two participant galaxies in a merger have combined into a new sort of self-governing system. And these systems are actually really difficult to find. So in contrast to spectroscopic pairs, which you can identify using statistical methods, post-mergers are not spectroscopically distinct by definition because they're a single galaxy once again. And they are also sort of morphologically degenerate, morphologically confused with a lot of other classes of galaxies. To name one, there's a huge degeneracy between the appearance of a galaxy that is currently experiencing an interaction and a galaxy that has completed an interaction, a post-merger. There are also imaging artifacts, morphological kind of dynamic range of the effects brought on by a galaxy merger, which make these difficult to identify. And so in the literature, we can get kind of these narrow windows, these sort of specific glimpses as what's happening in galaxy post-mergers. But all of these studies, including my own, actually have to come with these caveats saying, you know, this is how we selected this post-merger sample. And it's quite difficult to make general claims about what happens in the post-merger epoch because of the selection effects brought on by the rigmarole, basically, of selecting galaxy post-mergers. And what I say here is that machine vision methods offer some hope for this. And this is what I've been using to identify galaxy post-mergers. And I can sort of tell you about how that's working in the context of this study. I've selected a couple figures for this context slide. The first one is from a colleague of mine here at UVic. This is from Shoshana Byrne-Mamahit, and this is a submitted paper of hers, also a new result. And this is showing in illustrious TNG, this is TNG 100, the sort of demographics of luminous AGN in galaxies. And she's binned her galaxies into a few different categories. In the gray, non-interacting galaxies, so these are galaxies that are well separated from their nearest companion, they're not really on a collision course, and they haven't experienced a merger or an interaction for some time. Galaxy pairs, which sort of as you would expect, have one or more interacting companions, and galaxy post-mergers, which have recently completed a major merger event with another system in the simulation. And what she's showing here is that in bins of X-ray luminosity, the relative numbers of interacting and post-merger galaxies increases as a function of X-ray luminosity, suggesting that you need these interactions, or at least these interactions are one channel for triggering these highly luminous AGN in the simulation. And hopefully I'll be able to convince you that something like this is happening in the observations as well. Yes.
X-ray luminosity of what?
So, can you say that again?
X-ray luminosity of what?
Oh, yeah. So in the simulation, this is actually, this is a bolometric luminosity derived from the accretion rate of the black hole in the simulation. In the observational studies, I'm going to be showing just X-ray luminosities from the eROSITA space mission, which have been probabilistically associated with galaxies.
Thank you.
Of course. Yeah, and on the right-hand sort of figure here, this is one of my own. This is from, I believe, my 2022 paper on mergers and star formation, but this is kind of showing the way that we have been identifying post-mergers for these studies. And there are a lot of layers to this, and so we have these selection effects that I was talking about, but we've really done our best to find a balance of identifying a relatively complete sample and a sample that is pure, so not seriously contaminated with galaxies that aren't post-mergers or galaxies that aren't merging at all. And just to summarize this, what we're doing is we're using galaxy morphologies, so starlight distributions, taken from simulations, and we're using illustrious TNG as well for this, because we have some confidence in the sort of representative nature of the morphologies in the simulation and what we think galaxies, post-merger galaxies in particular, look like in the universe. And we use realism-added versions of those images to train a neural network, which we then apply to imaging from, this is, excuse me, this is unions, which is sort of a conglomerate survey in the northern sky. We particularly use R-band imaging from the Canada-France Imaging Survey. And we classify those galaxies. We look at the galaxies that get the highest machine vision predictions of post-merger status. And then we visually inspect or basically clean the sample by eye. And so in CFIS, we ended up with just shy of 700 galaxies. And this is actually not the sample that I'm using for this paper, and I'll tell you about that in a couple slides as well. But this is the method that we use for post-merger identification. For AGN in post-mergers particularly, I want to sort of suggest at least that there's reasonable qualitative agreement in the literature that interactions and mergers are a channel for triggering AGN in galaxies and altering their accretion states. So this is, we expect true of galaxies that are experiencing close interactions who have been tidally disrupted. Gas in those galaxies loses angular momentum and begins to fall towards the center. And we think that these effects once again peak in the post-coalescence epoch. So I've selected a couple figures. These are from a paper of my own that came out earlier this year. Here, what I'm showing is the excess, which is the relative incidence rate of AGN in mergers compared to control samples. And I'm looking at 3 different AGN types here. These are narrow line BPT AGN in the top panel. These are dust reddened mid-infrared AGN in the middle panel. And in the bottom, these are low excitation radio galaxies. So radio sources that we expect are corresponding to a galaxy in a sort of homogeneous, or sorry, I should say isotropic accretion state, usually a lower accretion state. And what we find in this study is that for our optical and our mid-infrared AGN excesses, that these types of AGN are preferentially being triggered in mergers. But for the sort of lower accretion states, we find that there isn't really a strong connection between galaxy mergers and the triggering of these types of AGN. Similarly, we look at the sort of accretion rate enhancement. And here in the observations, we measure that as luminosity in O3, the O3 sort of forbidden line. And we check again against a control sample, the luminosity of our interacting AGN. We compare those to the luminosities of non-interacting AGN. And what we find is that galaxy pairs have luminosities that are kind of consistent with what we see in non-interacting AGN. So that is to say that galaxy interactions, ongoing interactions, are sort of a way to produce a relatively typical narrow line AGN. But our post-mergers actually are around twice as luminous in these systems compared to controls. So there's sort of this idea that we're developing that the post-mergers are unique in their ability to trigger AGN, but also unique in their ability as far as the dynamic range of the AGN that they trigger. A problem with this study, and you'll probably notice that even between these 2 plots, there's a discrepancy, which is that a bunch of our AGN in this sample drop out. And this is a result of AGN selection effects. So in order to study AGN of a certain type, you have to draw all of these lines, many of them somewhat arbitrary, to select AGN of a particular type that are convenient for you to study. And we do this, or we try to work around this in this paper, the one that I'm showing the figures from here, by basically trying to study a bunch of different types of AGN at once and look for connections between those AGN classes. But
Another question?
of course.
P, how do you calculate that? And
Oh,
what is
yeah.
it?
Yeah, that's a great question. So we take the coordinates, RA and DEC, and the redshift of the galaxy, and we calculate an angular diameter distance at the redshift, and we use the angular separation and the angular diameter distance to calculate basically a 2D projected separation. So this is not a 3D distance. That's not really available to us in the observations, but it's an approximation.
And if it goes below 0, that means they're projected on top of each other?
Oh, yeah, sorry, that's a really good question. So on these figures, what I end up doing is I shade out the region sort of below 0, and I just plot my post-merger data points there. So to the left of 0 on these figures, they're actually not spectroscopically distinct galaxy pairs anymore. They're just systems that we identify using machine vision to be post-mergers.
And the excess that's there is with respect to?
Yeah, so we match a control sample on, in this case, or in the case of this figure, we match a control sample on redshift and stellar mass. So for each target galaxy, let's say it's a galaxy interacting in a pair between 0 and 10 kiloparsecs in projected separation, we look up a galaxy that is like well separated from its nearest companion. We expect non-interacting, that has a similar mass and a similar redshift. And we create these equal sized sort of samples of galaxy mergers and controls and take the ratio of the AGN fractions in those two.
Okay, so that's a straight ratio, not a percentage.
Right, yeah. So like an excess of 2 just means that there are like twice as many AGN in the interacting or the post-merger sample compared to a control sample that we match.
Thank you.
No worries. Okay, so yeah, the point that I was sort of reaching for with this slide is that these sort of, I'll say longer wavelength, even though we're talking about optical and mid-infrared, selection methods are highly sensitive to a lot of criteria that have very little to do with the actual status of the AGN in the center of the galaxy or of the supermassive black hole. So things like geometry, orientation, dust covering fraction, the sort of depth or the density of the dust column separating the supermassive black hole from the observer, all of these different things. And it would be nice to find a way to work around these, because we actually think that mergers are going to be sensitive to these orientation effects, particularly where dust is concerned, because we expect that there should be some either galaxy scale or even nuclear scale 3D distribution of dust as a result of the morphological disturbance that is taking place. So yeah, it'd be nice to work around this. And the way that we're able to do that in this study is using X-ray observations, which are available through eROSITA, and eROS-1 is the eROSITA All-Sky Survey first data release. The survey is the first one of its kind. It is an all-sky survey with approximately homogeneous coverage. There's a slight variation in the depth of the survey as a function of the latitude of the telescope in its orbit. It has a polar orbit, so the observations stack a little bit more densely near the poles, but it's not a super strong effect. Yeah, X-ray observations, because of basically the energy levels of the individual photons that are being observed, you can basically probe the accretion state of an AGN through obscuring dust, through like an obscuring narrow line region, for example, except when in cases where that obscuring material is Compton thick. And these Compton thick cases are really interesting to this study. But as far as we're concerned for counting X-ray AGN, these are cases that are essentially lost to us, not really unrecoverable, or essentially unrecoverable. Otherwise, though, X-ray is really nice for this reason, because even if you have a dusty AGN, you can kind of see what's actually happening with the accretion state, the supermassive black hole, through that dust. So this is really convenient for our purposes. This also has a reasonable overlap with SDSS DR7, which is sort of similarly like a flux limited or brightness limited galaxy survey. So these two are kind of compatible in that way. We get sort of this chunk of the SDSS DR7 polygon, which I'm showing in this just this map of the sky here, that is overlapping with eROSITA and also legacy survey data release 10, which in this case we're using for Deckel's imaging. The Deckel's imaging is important, even though there's SDSS imaging up here. Deckel's imaging is important for this study because the depth and resolution are significantly better than SDSS, and we use those to find our post-mergers in the study. So just to give a really quick overview of the data products, because there are a lot of different ones that are being folded into the study here, and I want to introduce everything before I kind of start throwing names of telescopes around or whatever. We have these eROSITA all-sky survey X-ray fluxes, which we can turn into X-ray luminosities, prepared by my colleague Mara Salvato at MPE. She does this by taking the most likely counterpart for each X-ray source on the sky. And if that most likely counterpart is a galaxy that's in my catalog, then I know about it. We also have optical photometry spectra redshifts and emission line measurements from SDSS DR7. And for the optical, we've also incorporated a broadline AGN catalog prepared by Liu et al. In 2019. They search for broadline AGN, so the signatures of these gas clouds orbiting close to the supermassive black hole, by looking for a broadened component of the H-alpha line in the optical spectra of these galaxies. We also use mid-infrared photometry from the WISE space mission, and we do this to look for dust reddening in basically in dust obscured AGN. So when you have a lot of dust in front of a supermassive black hole that's actively accreting, the sort of basically the ionizing radiation from the accretion disk is absorbed by the dust and then re-emitted at a longer wavelength such that it has a redder color in the mid-infrared. So we can take advantage of this. And a couple other sort of relevant samples. I have a galaxy pair sample for comparison against our post-merger class. And I also have a new post-merger sample, which I'm about to tell you about. One thing that I want to highlight here is that these are really luminous X-ray AGN. And part of this is because we're limited by the sensitivity of the eROSITA data. So we can only probe down to certain luminosities, but it allows us at least to look at kind of the most actively accreting galaxies at low redshift. And corresponding to these really bright X-ray luminosities here. So this new post-merger sample that I mentioned, on one of the first slides, I showed that flow chart that was describing how I identified a post-merger sample in the Canada-France imaging survey. And both CFIS and Deckel's, the imaging that I'm using for this study, have better depth and resolution compared to SDSS. This basically allows us to see, in a lot of cases, the merger-induced morphologies that we're looking for in these galaxies. So first, we trained this convolutional neural network, this machine learning model, and applied it to the Canada-France imaging survey. But for this study, CFIS isn't ideal for us because it's only available northwards of 30 degrees in declination. And if I go back to my map here, you can see that we would be missing out on kind of a lot of our sources, basically, most of this SDSS polygon, if we were to try to use CFIS for this study. In contrast, Decals is available for a larger area, and it does have slightly worse depth and resolution compared to the Canada Friends Imaging Survey by about 1 magnitude in the R band, and the pixel scale is about twice as large in Decals. So it's reasonable to assume that we should expect some loss of performance, some loss of post mergers, but it's worth checking. So that's what we did. And we ran some tests and showed that, likely because of the relatively shallower depth of the imaging in Decals, galaxies that appear in both surveys tend to get lower classification in Decals, lower post-merger predictions in Decals compared to what they would have gotten if they appeared in CFIS imaging. And I'll point out that this is log scale. If you don't put this histogram in log scale, it's very narrow. It's a super narrow distribution. We ran some additional tests as well, and we essentially found that this effect is sort of canceled out by the fact that, weirdly and in some cases inexplicably, galaxies that appear to be genuine post-mergers in some cases are identified in Decals imaging when they would have been missed in CFIS. Rarely, this has to do with an imaging artifact that appeared in the CFIS imaging, which is not present in the Decals imaging. But in other cases, there isn't a super good explanation for it, but we're getting free post-mergers out of it, so I won't ask too many questions. Here's a comparison of the two imaging surveys, and maybe I can let you all in the room try to identify which is which. These are both post-processing, so I apply the same normalization scheme to the Decals imaging and the CFIS imaging before I feed it into the convolutional neural network for classification. And you can see that, except in cases where there is an imaging artifact in one survey or the other, the appearances of the galaxies are pretty similar. One of them has a visibly larger PSF. The galaxies look a little bit fuzzier, but in most cases, I would say in all of these cases, actually, the morphological sort of signature of the merger that you can see in the CFIS imaging is still present in the Decals imaging. Any guesses as to which is which? Maybe it's the Zoom call quality, but yeah, CFIS is on the top and Decals is on the bottom here. But it's really quite close after you sort of normalize them in the same way. So we find some new post mergers, and we actually get more out of Decals than we found using CFIS, which is nice. And this is just to do with the proportion, like the total number of galaxies that we're looking at, and the number of galaxies that get these high post merger predictions. So I went through 4,100 galaxy images a couple months ago, and confirmed by eye 924 of them. So it's a relatively conservative sort of predicted post-merger fraction within the machine predicted sample. But the Decals imaging does make it a little bit more difficult to really convince, or it made it difficult for me to convince myself of merger statuses in kind of ambiguous cases. And we wanted to make sure that we had a really pure post-merger sample here. So we end up with these kind of more dramatically disturbed post-mergers, which I'm showing in this mosaic here. What are these post-mergers like? So something that I will point out, and this is a reassuring result, is that the visual agreement fraction, so this is the proportion of the time when I agree with the neural network, increases as a function of the value of the neural network's prediction of post-merger status, which is to say that even in Decals in a different imaging sample, the model still seems to have some grasp of what's going on, and that's comforting. we find, as we did in Cephas, that post-mergers are typically more luminous, and as a result of that, found at slightly higher redshift on average compared to the general galaxy population. And this is sort of a consequence of the fact that if you have a more massive or a brighter galaxy, any sort of low surface brightness extended tidal features associated with a merger event in that galaxy are going to be more visible, brighter against the noise, basically. So there is this bias towards brighter, more massive galaxies in our sample. So yeah, I'm showing the redshift distributions of the mergers, and the same in R-band absolute magnitude, which at the moment I'm using as a proxy for stellar mass, rather than using any stellar mass catalog. And the reason for that is that stellar mass catalogs are typically not available for galaxies that host broad emission lines in their optical spectra. This is something that we're working around, and I'll mention a couple notes about that at the end. We may have galaxy stellar masses for these for the entire catalog pretty soon. A few words about the AGN sample. So these are kind of various other AGN catalogs plotted on a histogram of their X-ray luminosity. And what I'll point out on this slide, because I definitely want to make sure that I get to some of the more interesting results, are that our BPT AGN, so ones that host narrow optical emission signatures of having an AGN, are typically a little bit less luminous than AGN that are appearing as dust obscured or dust reddened, which are themselves slightly less luminous as the X-ray AGN that we're identifying as broadline region AGN in the optical. And this kind of makes sense, just as consistent with the idea that at some X-ray luminosity, you expect that the feedback on sort of a nuclear scale associated with the accretion that's taking place has a higher chance to effectively blow out obscuring material and reveal the broadline region and even the accretion disk emission to us as we're trying to observe these galaxies in the optical. But there's a lot of overlap between these classes. We can also plot all of these various classes on the BPT diagram, which a couple other studies have done. And what I will point out here is that our BPT AGN are taken from the Keeley 2001 criterion region of the BPT diagram. So these are really certain AGN. We're pretty sure that these are not starburst galaxies, for example. But the positions of these are just by definition, because we use this diagram to select them. What's interesting here is that the X-ray AGN, many of them appear as sort of composite galaxies on this diagram, and many of them appear as star forming as well. And this is a result that a colleague of mine, Chris Agostino, who recently finished his PhD at Indiana University, pointed out in a paper of his, showing that basically the BPT diagram, because of the selection criteria requiring the presence of an observable narrow line region, can't pick up on everything that actually has an accreting supermassive black hole. This could be because of dust obscuration. It could also be just because of a relatively weak or underluminous narrow line region. Yeah, and similarly, I'll point out here that the mid-infrared or dust obscured AGN that also happen to have an observable narrow line region belong sometimes to the AGN classes on the BPT diagram, sometimes to the star forming classes. And it's somewhat similar with the galaxies hosting broad emission lines, where we can still measure a narrow component. They kind of appear as various different sort of classes on the BPT diagram, although this is a little bit trickier to interpret because when you're decomposing an emission line into a broad and a narrow component, there are some difficulties in trying to do that accurately. For mid-infrared color of the sample, I'll just point out that, once again, using mid-infrared color is nice, and it's a complementary sort of AGN criterion for this analysis. But many of our AGN, which we know to be actively accreting on account of, for example, X-ray luminosity or narrow line emission or even broad line emission, fall below the color criterion that we use to select mid-infrared AGN. And this is just to say that not everything has the sort of obscuring dust and the dust reddening effect that we need to be able to observe an AGN in the mid-infrared in this way. So I've got this Venn diagram here, which sort of shows the different AGN selection. What I'll point out, a couple things about this, is that there are no sort of pentuple class AGN, and this is just because of the fact that low excitation radio galaxies, and I actually can't see my own color scale here. Low excitation radio galaxies, which are in the brown, basically do not coincide with BPT AGN, sort of by definition. And so there's nothing in the middle here, but there are a lot of broadline AGN shown in the green and X-ray AGN in common. And there are also a lot of BPT AGN and mid-infrared AGN in common. So there's significant overlap between these classes. They're all kind of probing different things about the AGN in these galaxies, but these can only ever be complementary to one another. There isn't really a single selection that's going to get everything for you. Okay, so now getting into some science results, and thank you for bearing with me all that time. Here is my sort of AGN observability study. So what I'm selecting here are galaxies that have an X-ray luminosity in eROSITA, and I'm plotting the fraction of those galaxies that can be observed as either a broadline galaxy, a mid-infrared galaxy, a BPT AGN, or in this plot, a low excitation radio galaxy. Eventually, we sort of find that there isn't really a strong coupling between these other AGN classes and the low excitation class. And so this is sort of dropped from the analysis later on, but I'm including it here just to illustrate that point, that these low accretion systems aren't really strongly connected to the X-ray AGN class. But what I think is really interesting about this plot is the kind of takeover of broadline AGN at a luminosity of somewhere between 10 to the 42 and 10 to the 43. They really start to outpace all of these other AGN classes. And I think this is likely evidence for dust blowout somewhere around this AGN luminosity. So sort of small scale or nuclear scale feedback changing in an active way the observability of the supermassive black hole associated with that object. What about merger status? So we can make this same plot. And this is actually my sort of attempt to make something mirroring that figure that I showed on my first slide from Shoshana Byrne-Mamahet as far as interaction status as a function of X-ray luminosity, and my X-ray luminosity here from the observations instead of from illustrious TNG. And what I'm able to sort of find in this sample is that the isolated class, and this could be a selection effect. I think selection effects are definitely part of it, but our isolated class is effectively in the majority for all X-ray luminosities. So we're either not successfully identifying them as interacting or post-mergers, or they are truly isolated. But I think the interesting result on this plot is in the relative dominance of galaxy pairs and post-mergers at different luminosities in X-ray. So for lower X-ray luminosities, below something like 10 to the 43, we see that pairs are typically more common. There's a higher pair fraction compared to the post-merger fraction at these luminosities. But around 10 to the 43, which is also interestingly enough, where we see that turnover for broadline visibility of AGN, we also see that our post-mergers become more common per capita than our galaxy pairs. And this is beginning to suggest a connection between galaxies with broad emission lines, galaxies hosting luminous X-ray AGN, and the post-merger class specifically. So we can begin to sort of get at this in a more statistical way by making an excess plot, sort of in the style of what I showed earlier on in the presentation from my previous paper. And what we find is that there are excesses of X-ray AGN in post-mergers and in galaxy pairs. There is a typical excess signal of around 1.5 for rather close galaxy pairs. So in this case, they have separations below around 80 kiloparsecs in projected separation. There's also a stronger signal, an excess of around 2 in this 924 galaxy post-merger sample that we find compared to controls that we match to those galaxies. Which is really interesting. Basically, it's suggesting that if you have a completed merger event, that galaxy is effectively twice as likely to host one of these X-ray AGN than any old galaxy that you would take. So what we find also is that the inverse, or I guess the orthogonal question, is also true, in that if we take a sample of eROSITA AGN and match them to on R-band absolute magnitude and redshift to a sample of galaxies that are not hosting AGN, that post-mergers are around twice as common in the AGN sample compared to an inert or a quiescent sample, basically. So in this sample, we do find this really strong and sort of bidirectional merger X-ray AGN connection. What about the accretion rates of these AGN? So what I find here is that pairs, at least in the way that the analysis is sort of shaking out right now, pairs are typically underluminous compared to systems that are hosting X-ray AGN but appear to be in non-interacting galaxies. And this is sort of consistent with this result, right, where we're seeing these non-interacting galaxies kind of across the X-ray luminosity dynamic range, but the galaxy pairs belonging typically to these lower X-ray luminosities. This shows up in this plot as well. So we're seeing that the galaxy pairs have kind of a suppression in X-ray luminosity compared to galaxies that have somehow been triggered into an active accretion state or a high accretion state through some secular means, like a morphological disruption due to a bar, something of this nature. So these secular events seem to be a little bit stronger or a little bit better at triggering these high accretion state AGN compared to galaxy pair phase interactions. And it could just be the case that the sort of tidal torques aren't strong enough in these interacting galaxy pairs to usher in the types of accretion rates that would be required to kind of get them above this line. But this actually changes in our post-merger sample. So our post-mergers are overluminous compared to secular and, as we can see, compared to interacting systems. They're about 3 decs higher in luminosity, which is a factor of 2, or sorry, 0.3 decs higher in luminosity, a factor of 2, compared to an isolated control sample that we match. And this sort of mirrors what we found with O3 luminosity earlier in the year. It's nice to find this connection because there is, we expect in systems where we can observe both O3 emission line luminosity and X-ray luminosity, there's a decently tight correlation between the two. And so it's good that we back out a similar result here, or reassuring at least. I'm going to talk about this a little bit, and this is one of the more kind of novel results that we've been able to produce with this data. So this is on specific observability of X-ray sources. So we're asking the question here, if we can observe a galaxy as an X-ray AGN, what are the chances that we can also observe it as either a narrow line BPT AGN, a dust reddened mid-infrared AGN, or a broad line AGN with some broad component in its H alpha emission. So we conduct this analysis, and we do this in the way that I have it set up currently in 3 bins of interaction stage. So I have sort of better separated pairs with projected separations between 40 and 120 kiloparsecs, close galaxy pairs with separations below 40 kiloparsecs, and once again, this post-merger sample that I identified in decals. And there are some interesting trends that fall out of this, and we're still kind of working on the best way to present these trends. But for now, I'll share this with you, which is that based on the statistics of our interacting galaxy pairs, it appears that X-ray AGN are no more likely to be observed as a narrow line BPT AGN in galaxy pairs compared to in isolated galaxies. And you can kind of see this in the sort of relative shapes of the Venn diagrams in the top row of the figure here. While the total numbers change, the kind of relative sizes of the X-ray AGN circle and the BPT AGN circle remain relatively constant. And also the overlap between those 2 classes remains pretty similar, regardless of what merger stage we're looking at here. This is implying that the observability of a narrow line region is mostly governed by secular factors, even in interacting galaxy pairs. And for mid-infrared, what we find actually is a stronger result. So we're more likely to see galaxies as dust reddened mid-infrared AGN in close galaxy pairs and in post-mergers. So the sort of increasing overlap from right to left in this middle panel is suggesting that more and more of our systems that are actively accreting, et cetera, are also experiencing degrees of dust obscuration as the merger events progress. And this is expected from some other results that we've seen on account of the idea that dust is being distributed sort of spherically in such a way that the likelihood of us observing a supermassive black hole sort of source or an accretion disk source behind some dust, being able to measure a dust reddening in that galaxy, that likelihood increases as the merger progresses. I think one of the most striking results that we see in this study is this really strong connection between broadline galaxies and specifically the post-merger epoch. So the X-ray AGN in our sample are far more likely to have an exposed broadline region or accretion disk in the post-merger epoch. And if you sort of do the statistics on this, and we've matched control samples for these, it's not any more likely to host a broadline region in galaxy pair interactions, but this changes very dramatically and suddenly in the post-merger epoch in particular. So again, this line connecting post-mergers, really high luminosity X-ray AGN, and the observability of a broadline region. And what I hope to argue is that this is evidence for, at the final stages of a merger, feedback, blowout of obscuring material in basically near the nucleus of the galaxy, resulting in the observability of a broadline region in post-mergers. So I could say a little bit about ongoing and future work, but I do want to make sure that I leave at least several minutes for time. So I'll really breeze through this and say that in order to improve on this, we will eventually need to improve on our merger identification, because we're getting all of these really nice data products, all sky surveys in X-ray, forthcoming LSST, et cetera. And so it's really important for us to be able to find post-mergers so that we can study their characteristics in all of these really rich sort of data products that we're about to have. My post-merger identification approach is currently being optimized. And I'm working with a colleague of mine, Leo Ferreira, also a postdoc here at UVic, to optimize this basically using a really massive training data set that we generated. So I talked about making mock observations earlier. We've made a mock survey called Mega Mock Cephas, wherein we have observed every galaxy in Illustris TNG in a grid of 20 redshift points and 4 camera angles for the entire basically 300,000 plus galaxy sample that comes out of that simulation. And we're using this as training data to try to prepare a model to classify mergers globally in the Canada-France imaging survey. And so this is a screenshot from like a web tool that Leo has created for this project, showing basically, without doing any visual classification at all, this really strong separation he's getting in parameter space between post mergers and non-interacting galaxies, basically. Also, I mentioned earlier that we're trying to get stellar masses for these galaxies. I'm working with Professor Samir Salim at Indiana University, who's responsible for the GSWLC stellar mass catalog. Working with him to produce stellar masses for these galaxies that I'm studying so that we can kind of compare them in a way that is a little bit more trustworthy and confident instead of just comparing the R-band absolute magnitudes of everything. And also, I think something that's really important for all of these studies is merger incompleteness, understanding what mergers we're missing and why. And there's a forthcoming paper from Scott Wilkinson. I've highlighted a figure here showing basically the classification accuracy of a random forest as a function of depth, imaging depth, and PSF resolution, and showing how basically PSF and depth govern our ability to observe galaxy post-mergers. And yeah, we'll have a serious effect on the completeness of any merger sample that we're able to identify. So I will stop there and take questions. Thanks.
Thank you for the talk. If there's any questions, I guess. Raise your hand. If there aren't any right now, I have a question. Can you hear me all right?
Yeah, I can.
If you go back to the lots of Venn diagrams, so the one big
Yeah.
Venn diagram.
Oh, the
That one, yeah, that's one. No, the other one.
oh, sorry.
I find it interesting that you have like fractionally more X-ray detected AGN that are also in mid-infrared, which kind of tells you they're dusty. But also you say that you have more X-ray AGN, which with broad line regions, which implies that you're blowing out or destroying the dust. How do you think the two like agree with one another?
Yeah, so I think what makes this analysis a little bit complicated and sometimes frustrating is the fact that all of these different AGN criteria are semi-arbitrary lines that we're drawing on a continuous variable. So for example, for the BPT AGN, we have to choose some signal to noise for the emission lines. For the mid-infrared, we have to choose some color criterion. And so there are a lot of cases where you have simultaneous observability of BPT AGN and basically dust obscuration of the AGN. And I think these are kind of like coinciding more frequently in the post-merger class. And in fact, I have a result, not in this presentation, that shows that they do coincide somewhat more frequently in the AGN class. So I think I also think of these two, the narrow line region AGN and the dust, as sort of mutually sort of exclusive. Like if you have something that's super dusty, you're less likely to see it in the optical. But in practice, the edge cases and the double detections end up kind of canceling out this effect, at least with the criteria that we've chosen.
And do you know what's the overlap between the WISE, X-ray, and broadline? Are there any galaxies that are all three?
WISE, X-ray, and broadline. I believe so. Yeah, maybe. So I'll go back to this, and I'll add as well that we're also changing our WISE criterion. We got a bit of feedback about the fact that the original WISE survey data products are more likely to have kind of blended colors in galaxy pairs. So effectively, if you have a close galaxy pair, that there's a greater chance of the photometry from two sources being blended into one. So we're using unwise now, and the results for that are also kind of forthcoming at this time, but the trends are holding up, broadly speaking. So you asked about simultaneous broadline, X-ray, and WISE, right? So that would be broadline, X-ray, and WISE. Yeah, this is not a super easy figure to read, especially live. Okay, so I think we would be here. Nope.
I think I see it's the 70.
Oh yeah, I think it's this group here, right? Yeah. So there are a decent number of them. It's comparable to the number of double detections for X-ray and WISE, actually. So around half, I guess, of the galaxies that are double detected between mid-infrared and broadline are also AGN detected, X-ray AGN detected, something like that.
That's really cool. I like the Venn diagram, even if it's hard to read. Mike has a question.
Yeah.
Hey, Bobby, can
Hi.
you go back to the very first plot that you showed by the other student?
Oh yeah, Shoshana's plot, right? This one?
She's no longer student.
Yes. Actually, I think she may be on her way to visit this week. I think she flew out this morning.
So these this is not a log scale or anything. So these fractions, this is from the simulation, right?
That's right.
And so these fractions are quite high that are in post mergers and pairs. But then in your results from the observational data, although they're enhanced in mergers, it's still, most of them are isolated, right?
Right. Yeah.
So what do we take from that comparison?
Yeah, I think that's a really good question. What I expect is driving the effect here is actually a couple of different things. So for our galaxy pairs, we expect that the galaxy pairs that we are recovering using spectroscopic methods are representative of the class. But due to fiber collision in SDSS, particularly as you get to closer and closer galaxy pairs, you're less likely to actually resolve it as a galaxy pair. So we know that we're losing a bunch of our galaxy pairs in that way. I'm also incredibly confident that we're losing a bunch of the real genuine post mergers in the sample. Meanwhile, in the simulation, this is sort of not a concern, effectively, in that you can just go to the metadata and say these two galaxies merge in snapshot X, and et cetera. So I think it's completeness as far as being able to identify the merging classes. My expectation would be that that's the driving force here. That's a good question. Thank you.
James has a question.
Yeah, could you just go back to the thumbnail you had of the systems you identified?
Oh, yeah, sure. I can do that. Here we are.
Yeah. So, I mean, some of these look like there may be more than one kind of thing. There were a few that looked like they had, big tidal features crossing them and so on. I mean, do you have a sort of more detailed sense that these are all really similar objects?
Right. So if I'm understanding, you're asking about kind of like the intrinsic diversity in the post-merger class, right?
For instance, the merger mass ratio, like, do you have a sense of, because there are one or two of them where I see what look like fairly narrow tidal streams that go across the middle of the object, but look like a lower mass,
Right.
merger.
Yeah, that's a really good question. So I think there are there's certainly a range included here. What I can say is that we train the model to identify merger mass ratios between 0.1 and 10. So basically within a 10-to-1 merger mass ratio, we are training our model to identify those. And we know that in the simulation and some test data, the model identified mergers pretty uniformly across that mass ratio, except for the lowest bin, the performance was a little bit worse. But we were getting high 80s, low 90s sort of accuracy. Now in observations, we have no idea if the completeness is anything like that, because we don't have any like metadata to study what's actually happening. We expect merger mass ratios between 1 and 10, but there's also this really strong degeneracy in the post-merger class between the recency of the merger, the merger mass ratio, and even the orbital parameters associated with the merger event. So all of these different things are kind of getting folded into one chance that our model gets to try to identify each of the galaxies in the survey as a merger or not. And we expect, for example, because of orbital parameters and timescales, that we're sampling sometimes below and sometimes above our nominal expected mass ratio regime.
And you don't get the merger parameters out, you just get the probability it's a post-merger.
Yeah, that's right. Although what I'll mention is that in that project that I showed the little web tool from in my last slide, Leo is actually, because of the size of the data set that we've generated, it's some terabytes of just galaxy merger images and isolated galaxy images. He's been already pretty successful in distinguishing between merger timescales. So if you throw enough data at it, you can do a lot more. But for this project, we sort of just wanted to give it our best shot to identify as many solid post mergers as we could. And yeah, like I said at the beginning, kind of acknowledge the various biases that we incur in doing that.
One more question, Brian.
So your ability to identify these depends critically on the simulations. What do they look like?
Yeah, that is a good question. I actually don't have any examples of simulated training data on hand. I think, yeah, sorry, go ahead.
Do they look like the systems you just showed? What is the...
Yeah, I would say, so we've done this a couple times internally in our group, is that we generate these mock observations using real skies from the survey that we're using. We choose redshifts that are realistic from the range of galaxies in the survey, draw PSFs, like real PSFs at random. So we make all of these kind of data choices to treat the starlight from the simulated galaxy in an accurate a way as possible to make it look like it's come from the survey, from the survey. We've sort of internally done like these, which one is real, which one is fake sort of galaxy tests amongst the people in our research group. And pretty much every time we find that to the human eye, they're indistinguishable. That's different from saying that they're statistically indistinguishable, or that there aren't any systematics that are associated with making a mock observation and hoping that the model will be able to classify real galaxies. All we're really able to point to is the fact that it seems to be able to do so. And visually, and as far as non-parametric morphologies and resolution, that the simulated galaxies look pretty similar. So yeah, it's our best attempt with the simulated data.
Thank you.
Of course.
All right, if there are no more questions, the pizza is here, so we gotta run. Thank you so much for
Okay.
your time.
Thank you all. I appreciate it. Enjoy the pizza.